Hello everyone, welcome to this lecture of the course Digital Electronics and Digital Circuits, and in this particular lecture we will be talking about combinational circuits, and we will be beginning a discussion of combinational circuits using XOR and XNOR gates, right? So the topic of discussion would be combinational circuits, right? Just to touch upon the basics, right, as we discussed in one of our beginning lecture that there are two kinds of circuits, one being combinational and another being sequential. We said combinational circuit are the ones where output depends upon present inputs only. Basically it's dependent, so basically we can say it's proportional or it's dependent upon set of present inputs. And so basically if we have to draw a block diagram of a combinational circuit, it would be something like this. So basically we say that this is a combinational logic, right? So basically it's like a combinational circuit, and when we say it's like a combinational circuit, we say it might have x number of inputs, right? X inputs, and it might have y number of outputs. There is no relation like that x has to be greater than y or y has to be greater than x. X and y are independent of each other in terms of number of x's and y depending upon the combinational circuit, and your present output will depend upon set of present inputs, basically saying that there is no memory element involved over here. So depending upon the input, your output would change, right? Now these are the combinational circuits, and to begin with, right, we will talk about we have spoken about various gates like AND gate, OR gate, NOT gate, NAND gate, NOR gate. All of them are combinational circuits only, and now we will talk about a important gate which is usually called as XOR gate, right? And we will talk about XOR operation as well. So basically XOR gate is something which we denote like this, right? Basically something like this. This is XOR, and then we have a one more gate which we will be discussing in this lecture. This is called XNOR gate, and XNOR gate is something like complement of XOR, and this is something like XNOR gate, right? So once we talk about XOR gate, right? So and we denote this XOR operation by using this symbol, like we denote AND by using dot, and we denote OR by plus, we denote XOR by plus in the bracket. So this is like XOR operation, this is like OR operation, and this is like AND operation, right? If we look at XOR function, right, XOR function is something which is something like where we say we have two inputs x and y, so we would say x or y would be equal to x by bar plus x bar y, correct? So this is my XOR function, and my XNOR function is, if you have two inputs x and y, would be like it would be complement of x or y, which would be equal to x by bar plus x bar by whole bar. If we open it and we simplify this expression, right, this would come out to be xy plus x bar y bar. So this is something which we should remember, like XOR gate function is something like XOR by, which is xy bar plus x by x bar y, and similarly XNOR is xy plus x bar y bar. And if one more thing, right, if we draw a circuit for this particular operation, right, where we say we have xy and we have z as an output, we have four set of inputs, four combinations of inputs, and if we calculate xy bar for this, when both are 0, it will be 0. When x is 0, first operation is 1, second would be 1. Similarly, this is 1, this is 0. Right? So basically for XOR gate, output is equal to 1 when both the inputs are different. When both the inputs are same, the output is always 0. And this thing is reverse for XNOR operation, as this is not of XOR, where we say that whenever the outputs are same, whenever the inputs are same, output is 1, otherwise the output is 0. So this is one of the important criteria to understand in this case, like xy bar plus x bar y means this is like summation m of 1 and 2, which means that output is 1 when both the inputs are different, output is 0 when both the inputs are same. Right? Now let's look at some of the interesting XOR properties, right? Some properties of XOR gate. Okay, so one of the properties is any number when we XOR with 0 would be equal to what? We said XOR with Y is X bar by plus X by bar, right? In this case, anything which is XORed with 0, the number would be X itself. Because in this case, this will become X bar into 0 plus X into 1. So this will be equal to X. Similarly, any number which is XORed with 1 would be equal to X complement, because what we saw is if the number is same, output is 0. If the numbers are 0, like if the numbers are different, output is 1. If X is 0, output has to be 1. If X is 1, output would be 0. So X XOR with 1 is X bar. A number XOR with itself will always be 0. This we have already seen. And a number which is XORed with its complement will always be equal to 1. Correct. And then the remaining properties of associativity and commutativity holds good for XNOR operations. XOR operations are well. So basically what I mean is if they are like, if we have three operations, right, three input variables, something like this. Say we have XOR with Y, XOR with Z, right? And we have like associativity, and we simply say this is equal to XOR with Y, right? And same is with the commutativity, where we say order doesn't matter, right? These are few important properties of XOR function, where we say any number XORed with 0 is a number itself, any number XORed with 1 is complement of that number, number XORed with itself is 0, and the number XORed with its complement is 1, right? Now let's go further and let's look at a 3 input XOR gate. Right, if we have 3 input XOR gate, we will have 3 inputs A, B and C. We will have an output 0. What all possible input combinations are there? I am just listing them now. Now 3 input XOR gate is something like my output Y is equal to A XOR with B XOR with C, right? And how do we calculate this? All A XOR with B is same as, like, this will be same as you A XOR with B using associativity and commutativity, right? And what is a 0 XOR with 0 is 0, and the output 0 of this should be XORed with C is again 0. 0 XORed with 0 is 0, and then XORed with 1, 0 and 1 is 1. Similarly, this is 1. 0 XORed with 1 is 1, 1 XORed with 1 is 0. This is 1, this is 0, this is 0, and then this is 1. Right? So basically what I can say, I is equal to summation of M of 1, 2, 1, 2, 4 and 7. Correct? This is correct. And how do we represent this in form of a K-map? This is represented in K-map like this, where we say that we have A here, B and C here. We would say something like it's 0, 1, 2, 3, 4, 5, 6 and 7. So this is how we will represent a 3 input XOR gate on a K-map, right? And there is a name nomenclature for this. This is known as odd function. See the zigzag formation over here with 1, 2, 4 and 7. This is called as an odd function, right? Similarly, if we look at XNOR operation, right? In XNOR operation, we will have our output, let's say Z, which will be equal to 1, 0, 0, 1, 0, 1, 1, 0, where Z will be equal to XNOR, and that will be equal to summation of M of 0, 3, 5 and 6, and this is represented by following in K-map: 0, 1, 2, 3, 4, 5, 6 and 7. This is nothing but this is called as an even function. Correct? So basically, if I have to draw it, correct? If you have to draw 3 input XOR gate, this will be something like this. we have A, B, C and Y. This is XOR gate, which is like a odd function, correct? And then we have a XNOR gate, right? Not of or at the end. So this is something like XNOR. What we do is we XOR A and B. We XOR with C. This is even function, right? So basically, this we talk about three input variable and odd function. If we draw it on the four variable map, right? If let's assume we have four variable input variable A, B, C, and D. How will the odd function be looking like? This will look like something like this. Starting with here, so this is like three input, and then we will have something like this. Similarly, four input even function would be something like complement of this. This would be equal to 1 1 1 1 1 1 1 1. This is like four variable A B C D. This is again four variable A B C D. Odd function and even function. Right? Now, why we are talking about these two properties of XOR gate or XNOR gate, odd function and even function? Because this property of XOR and XNOR gate is used for something called as a parity generation and correction. Correct? This particular thing is useful in error detection and correction. And how do we say that, right? So what we do is we will be looking at two things. One is parity generator and parity checker. And just to tell you, right, what is a parity bit? Well, there is one term called parity bit. This is an extra bit which is included with a binary message. Let's look at this, right? Let's assume that I have a three input signal. Let's assume I have a three input signal called X, Y, Z, right? Which can have these set of values. I'm just quickly writing them down. Now let's assume I add a parity bit, P parity bit, and let's call it a even parity. Even parity in the sense like if we add this bit into the circuit and we XOR X, Y, Z with P, the output would be an even parity, right? So let's assume we have an even parity bit. So even parity bit for this would be output of this is 0. Even parity would be like XOR of all these three functions, which will be 0, 1, 1, 0, 1, 0, 0, 1. Right? Now what we will do is, this is like our parity bit. So this is a parity which we will generate, and our parity bit would be nothing but X, Y, Z. Right? And when we say that how this helps us in error detection and correction is, what we would say is our error correction code is nothing but X or with Y, X or with Z, X or with parity bit. This should be equal to 0. If this correction code is any value other than 0, if it is 1, then it means that there is a problem in the data transfer, problem in the code. If I saw everything, right, what it would be? It would be 0. It would be 0, 0, 0. Everything would be 0 over here. 1 or with 0, 1 XOR with 1 is 0, 0 with 1 is 1, 1 with 1 is 0. So if there are no if there are, so basically if I have to send a message, if I have to transfer this message comprising of XYZ, so what I would do is, instead of sending only XYZ, I will send 4 bits. X bit, I will send a message as X bit, Y bit, Z bit and PE bit, which I will create using this circuit, right? And once I send it right at the receiver, and what I will do is I will XOR all these 4 operations, and if all these 4 XOR output is 0, then I would say message is correct. If the output is not 0, I would say there is a problem in the data transfer. So that is the concept of parity generation and parity correction. correct? So our parity bit code would be XOR of 3 operation. It would be something like this. So my parity generator code would be something like this is the PE bit X, Y, Z, and my error correction circuit. So this will be on the sender side where I am sending X, Y, Z along with P, and on the receiver side I would have something like X, Y. I am receiving Z and P. Then this will be XOR again corrector. So this is on the receiver side. If C is not equal to 0, then there is an error in transfer. Correct? So this is a concept of XOR gate and XNOR gate. And just to revisit this concept, we spoke about combinational circuit where output is proportional to set of present inputs and it depends upon present inputs only. Then we talked about XOR and XNOR gate and we spoke about the functionality of these two where XOR is equal to XY bar plus X bar by, which simply means the output is equal to 0 if both the inputs are same, and if both the inputs are different, output is equal to 1. XNOR is opposite where both the inputs are same, output will be 1, and if both the inputs are different, output would be 0. Then we spoke about a few properties of XOR operation, and these are the important properties which makes XOR gate stand out as compared to other gates. Then we spoke about 3-input XOR gate function, and we spoke about how it's an odd function and how XNOR is an even function. Then we implemented both odd and even function, and we drew it for 4-variable map as well. Finally, we saw what is the application of this particular odd function and even function. Basically, the application is in parity generation and parity correction. So basically, if you have to send a message, transfer a message, we add a parity bit, and a parity bit could be an even bit or an odd bit. If we add an even bit, it's like parity even bit is like XOR of all the threes. If it is an odd parity, is XNOR. And eventually, once we are sending an even parity bit with a normal data, if we at the receiver side, if we do a XOR of all the 4 bits, right, X, Y, Z and PET, if the correction code is 0, it means the data has transferred properly. If the correction code is 1, it means the data, there is an error in the data transfer. Correct? This is what we show as an saw as an implementation quickly. Right now, moving forward, right, I wanted to talk about one example where we have like BCD and one circuit implementation for our combinational logic. We have BCD nomenclature and we have XS3 code. Right? XS3 code is nothing but is equal to BCD plus 3. BCD plus 3. So basically, if my binary coded decimal is something like, say, my decimal digit is something like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. My BCD would be 0, 0, 0, 0. This would be 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1. My XS3 would be plus 3, right? So this would become 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0. This will be 8, this will be 9, this will be 10, which is A, this is B, and this is C. Correct? Now let's assume that this is a truth table and we want to form a combinational circuit where we can get, if we have this as an input, right, BCD as an input, A, B, C, D are input bits. I want to convert them into an output and the output should be an XS3 code, right? Let's assume the output is alpha, beta, gamma and delta. Correct? So can I draw a combinational circuit? If you remember in the beginning, we spoke about combinational circuit with something like this being a black box, this being set of inputs and this being your set of outputs, right? So now in this particular case, we have set of 4 inputs and we want a set of 4 outputs and we want to implement a logic where logic converts a BCD number into an XS3. So basically add 3 to BCD numbers and does an output. How do we do that? Now if you see, we have already drawn a truth table over here, where we said A, B, C, D are the inputs, alpha, beta, gamma and delta are the outputs. And basically what we have to do is, we will see alpha, beta, gamma and delta, all these four outputs will depend upon all the inputs. So basically, if I start drawing K maps, right, for circuit minimization, what I would say is, let's draw a K map for alpha. Right, this is A, B, C, D, 0 0 0 1 1 1 1 1 0 0 0 0 1 1 1 1 0. Right, now my alpha is what? Alpha is 1 for 5. So basically my alpha is summation m 5 6 7 8 9. My beta is summation m 1 2 3 4 9. Gamma is summation m 0 0 3 4 7 8, and my delta is summation m 0 2. Right, so basically m5 is nothing but 0 1 2 3 4 5 6 7 8 and 9. Right, and if this is my XS3 code, right, what do I do? What we can do is, we can do a circuit minimization over here. And if you see, right, whenever we are doing this conversion, like we can do proper grouping and stuff. So this is for my alpha, and similarly we can do for beta, gamma and delta. One thing to notice is, if the number is anything more than 9, right, everything else is don't care for us, right? If assume like there is nothing like BCD of 10, BCD of 10 does not exist. So output of 11 and everything does not make any sense for me. So all these things, 8 9 10 11 12, 13, 14 and 15 are don't cares for me. This is clear, right? I hope this is clear. Now if this is the case, what would be the circuit minimization for this? Circuit minimization for this would be simple. So for this 1 and 1, largest group of 2 raised to power 8 is this one. This is one circuit, right? Then for covering these ones, this is 1, this is third. So this would be equal to what? This will be equal to A plus, this is what, our B is constant B, and here D is constant BD. How about this? This will be equal to, here B is constant, and from here to here C is constant plus BC. Right, so if I say that my alpha is equal to A plus BD plus BC, if I do this implementation, I will get output of, I will get alpha as an output, which is XS3 output. Similarly, now if we have to draw the same thing for beta, right, what we can do is, we can again draw a K map for beta, and the K map for beta would be something like this. Right, as I said, all these things would be don't care, because inputs are not at all there. B will be 1 2 3 0 1 2 3 4 and 8 and 9. So what all possible combinations we can have over here? This is 1, this is second, right, and this is third. So in this case, my beta would be equal to B bar C plus B bar D plus BCD bar. Right, now if we move on to our gamma, gamma is, let's quickly do it, right? So basically all these are don't care. My gamma is summation of 0, it's 1 here, 1 2 3 4 5 6 7 and 8. Right, so basically this is one grouping and this is another grouping. So my gamma in this case would be what? C bar D bar plus this would be what, 1 1, this will be CD. Similarly, if we look at delta now, my delta was equal to summation of 0 to 3 0 to 4 6 8, 0 to 4, we have to draw it. AB CD 0 0 0 1 1 1 1 0 0 0 0 1 1 1, or 10 onwards, 8 9 10 11 12 13 14 15, everything was don't care, 10 11 12 13 14 15 were don't care, and then 0 is this one, 1 2 is this one, 4 is this one, 0 1 2 3, sorry, 4 is this one, 5 6 is this one, and 8 is this one, right? And what kind of a combination is possible for this particular set of numbers? One possible combination is this 4 plus 4 8 blocks, right? So my delta would become equal to what is common in these blocks. AB is changing, CD only last D bar is common, right? So delta is equal to D bar. So now if we put all these equations together, right? If we put all these equations together, I would say my W is equal to A plus BC plus BD. So basically W is nothing but what we call as our alpha. My beta is equal to what? B bar C plus B bar D plus okay, so yeah, so this will be equal to what we got in the previous foil, right? So what we got in the previous foil was B bar C B bar D plus B C D bar. Let us check. Yes, and gamma is CD bar plus CD. Gamma was CD bar. This was nothing but X naught, and my delta is D bar. Now, if we have to realize this circuit, right, what we can do is my if I have if I have four inputs, right, A, B, C, and D, my output. See, this is my circuit, right, and let's assume there is something called as D. So I will do naught of D, right, and let's assume that this is our black box. This is my delta. My gamma is nothing but, let's assume this is C. This is C bar. So basically my gamma would be C into D plus C bar into D bar. So basically C bar into D bar, and both of them OR together. So this will be my gamma, and so on and so forth. We can realize this circuit. So basically what I wanted to show using this particular example is that we have set of inputs A, B, C, D, and then we have set of outputs alpha, beta, gamma, and delta, and we have a set of relationship between all of them. And what we did was we created a K-maps for each output as a function of all the inputs, and once we did that, we got a minimized circuits for alpha, beta, gamma, and delta, and we were able to implement a combinational circuit, right? So this is all about it, right? And just for the sake of completion, I can simply show that this is nothing but this is a product of some terms. We have BC and it, then we have PD and it, BC, PD. Then at the end we have a OR operation of A. Then at the end we did a OR. This is my W. So this circuit would be implemented, and this is how we spoke about combinational circuits. And this is one example of a combinational circuit. Hope this lecture was useful and you found it useful. Here we actually walked through all the XOR and XNOR gates, and we actually took a combinational circuit and we derived all the outputs from my inputs and we implemented them as a form of basic gates. Thank you very much.